What you have to remember, under boiling point, when the number of carbon atom increases, the boiling point increases, and when the branching increases, boiling point decreases. Comparable masses, if we are taking of alcohol, alkanes, hydrocarbons and ethers, what happens? Alcohols is having the highest boiling point due to the presence of hydrogen bond. Alcohols reacts with highly electropositive alkali metals such as sodium, potassium, aluminum, etc. to yield corresponding alkoxides with the liberation of hydrogen. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 3 of the chapter Alcohols, Phenols and Ethers. So in the last session we discussed the different methods of preparation of alcohol, right? The first one was from alkenes. In that itself we studied 2 different methods. Then from carbonyl compounds. What were carbonyl compounds? Those compounds containing C double bond O, right? And then from Grignard reagent as well, and how you can obtain a primary alcohol, secondary alcohol, tertiary alcohol, right? Now in today's session we are going to study the physical properties of alcohols, then the chemical properties of alcohols. So by that we'll come to an end to the discussion of alcohols, then we'll move on to the phenols in the next session, right? So beginning with the physical properties of alcohols, alcohols consist of 2 parts, an alkyl group and a hydroxyl group. So what is the general formula we have already studied? It is ROH, right? So what it is consisting of, one alkyl group will be there, this R stands for any alkyl group, and then you have an hydroxyl group. So this is called as your alcohol, right? So the properties are due to the OH group. So because of the presence of this hydroxyl group, the properties arises, right? The alkyl and aryl groups modify these properties, and the boiling points solubility we are going to discuss now. The physical properties, boiling point and solubility, how it is in the alcohols we are going to see. So boiling point, the boiling point of alcohols increases with increase in number of carbon atoms. Okay, so the same we have studied in haloalkanes and haloarenes as well. When the number of carbon atom increases, the boiling point increases. Why is that? Because when the number of carbon atom increases, of course the mass increases, right? Molecular mass increases. So of course the boiling point also increases, as well as the van der Waals force of attraction as well as increases. Because of these reasons, when the number of carbon atom increases, the boiling point of the alcohol also increases. That means if you are comparing methanol and ethanol, just by looking at this we can tell that ethanol is having more boiling point. Why? Because it is having more carbon atoms. I hope it is clear, right? So this is due to increase in van der Waals forces. In alcohols, the boiling point decrease with increase in branching. Even this we have discussed in the last chapter. So when the branching increases, what happens to the boiling point? Boiling point decreases. Now branching increases means what? Now let's take the example of butanol. CH3, CH2, 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 OH. So this is the normal structure of butanol. Now I am going to write an isomer of this. So let's assume that this is going to shift here. So what will be your structure? CH3, CH3, and you have a CH2 here and OH. Right. Now I am going to write another isomer again. I am going to shift to this CH2 here. So what you are going to get? CH3, 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 OH. So as you can see, these are the 3 different isomers that I have mentioned here. So in all these cases, you can see when the branching increases, what is happening to the surface area? What is happening to the area? As you can see, it is this much big. From the diagram itself, you can say. From here, what happens when one branching has occurred? Yes, the surface area is decreased. Now, when the 2 methyl groups have become branches, what happens? The size has decreased much more. So the surface area, when it decreases, the boiling point also decreases because it becomes much easier to boil the alcohol then. So what you have to remember, under boiling point, when the number of carbon atom increases, the boiling point increases, and when the branching increases, boiling point decreases. Right? Okay. Now the reasons is that when branching increases, van der Waals force decreases due to decrease in surface area. This is what I discussed now. In alcohols, the hydrogen atom of OH group is bonded to an electronegative oxygen atom. Right. The general formulas are OH. As you can see, the OH bond we just discussed now, because of this hydroxyl group, the properties of the alcohols arises, right? So because there is an electronegativity difference between the oxygen and hydrogen, yes, as you can see there is an electronegativity difference. This bond is a polar bond, right? Oxygen-hydrogen bond, which you can see it is a polar bond, right? So therefore, it is capable of forming intermolecular hydrogen bonding. Now, how is intermolecular hydrogen bonding? What is intermolecular hydrogen bonding? Hydrogen bond can be formed between two different molecules, right? So intermolecular hydrogen bonding, how it is formed, it is shown here. So this is one molecule of alcohol. This is another molecule of alcohol. As discussed, there is an electronegativity difference between the oxygen and hydrogen atom, right, in the OH bond. So as you can see, the oxygen is having a partial negative charge because it is more electronegative, right? Hydrogen is having a partial positive charge because it is less electronegative. This shared pair of electron will be attracted towards the oxygen. That is why it is getting a partial negative charge. Now, moving on to the next molecule, okay, there also you can see hydrogen will have a positive charge, oxygen will have a negative charge. So now as you can see, oxygen is having a negative charge, hydrogen is having a positive charge. So there will be a bond formed between the more electronegative atom and hydrogen. So this dotted line you can see, that is the hydrogen bond which is formed. So this is formed between two different molecules. This is one molecule of alcohol, this is another molecule. So that is why it is called as intermolecular hydrogen bond can be formed, because there exist hydrogen bonds in alcohol due to this OH bond because of the electronegativity difference, right? Now, hence alcohols have higher boiling points than the corresponding other classes of compounds in hydrocarbons, ethers and haloalkanes and haloarenes of comparable molecular mass, okay? So if we are considering, example is just taken here, this is an ethanol, which is of course an alcohol, and methoxymethane. What is methoxymethane? It is an ether. This we will be discussing in the upcoming sessions. And then you have propane. So this is an alkane, this is an alcohol, and this is an ether. So all of them are having the same number of carbon atoms. Here you have 2, here you have 2, and here you have 2. So almost their molecular masses are similar. If their molecular masses are similar, then that means that of course their boiling point also should be almost the same. But if you are comparing alcohol with any other hydrocarbon, what happens? Hydrocarbon or ether, what happens? The alcohol will be having the highest boiling point, because in alcohols there is a special thing. What it is? Hydrogen bonds are present. As hydrogen bonds are present. That is what we just discussed in the previous slide, right? So hydrogen bonds are present in alcohols. Because of this presence of hydrogen bond, what happens? An extra bond is present, right? Already bonds are present, and extra bond is also present. So what happens? Yes, more stronger the bond will be, and hence it will be difficult to break the bonds so that the alcohol starts boiling. So that is why comparable masses, if we are taking of alcohol, alkanes, hydrocarbons and ethers, what happens? Alcohols is having the highest boiling point due to the presence of hydrogen bond. For example, ethanol and propane have comparable molecular masses, but their boiling points differ. The boiling point of methoxymethane is intermediate of the two boiling points. So I hope it is clear, right? Now, moving on to the next physical property, that is solubility. The solubility of alcohols in water is due to their ability to form hydrogen bonds. Again, the solubility, alcohols are soluble in water again because of the same reason, because it is able to form hydrogen bonds, right? With water molecules, solubility decreases with increase in size of the hydrophobic part. That means, as discussed, ROH, right? So when the alkyl group becomes bigger and bigger, that is from methyl to ethyl to propyl to butyl, if we are moving, when the alkyl group becomes bigger and bigger, what happens? It becomes lesser and lesser soluble, because this alkyl part is hydrophobic. It doesn't have attraction towards water. It hates water. That is this word stands for, right? Hydrophobic. So this alkyl part is the hydrophobic part. So what happens when this becomes bigger and bigger? The solubility becomes less. But alcohols are soluble in water because of the presence of hydrogen bond. As you can see, this is a molecule of alcohol which is shown here. Already, as we have discussed, because of the electronegativity difference, hydrogen will have a partial positive charge, oxygen will have a partial negative charge. And this is a molecule of water which is shown here, H2O. So here also hydrogen bonds will be there. Oxygen will have a partial negative charge. So what happens? This positive charge and negative charge will form a bond, which is the hydrogen bond. So because this hydrogen bond is formed, alcohols are able to be soluble in water. So next we are moving on to the chemical properties of alcohols. So the chemical properties of alcohols are mainly due to the presence of hydroxyl functional group. The reactions of OH group in alcohols may be divided into two types. So we are going to classify it broadly into two types, and then we are going to discuss the various chemical reactions. So the first one is reactions involving cleavage. What does cleavage means? It is breaking of oxygen-hydrogen bond, and the reactions involving the cleavage of carbon-oxygen bond. Okay. So for example, let us take the example of methanol, CH3OH. So it means that either there can be a cleavage of oxygen-hydrogen bond or carbon-oxygen bond. So this we are going to discuss in detail. So the first one, as you can see, reaction involving cleavage of oxygen-hydrogen bond. So in this case, the alcohol, yes, the alcohol behaves as a nucleophile. Alcohol will behave as a nucleophile. Nucleophile means it will have attraction towards positively charged species. Okay, so let's take an example of an alcohol. The general formula I have represented here, and an oxygen, it will have two lone pair of electrons, right? And a carbocation is present here. So in the first case, when oxygen-hydrogen bond is going to break, your alcohol will be behaving as a nucleophile. So as you can see, there is a positively charged species, that is a carbocation is present. So this is going to act as a nucleophile now. So the electrons will be donated to the carbon atom, and what will be formed? RO, and already a hydrogen is there and the carbon will be present. Now, what will happen to the positive charge? As you can see, the oxygen is donating the electrons to the carbon. So what happens? The oxygen will get a positive charge. Of course, the oxygen doesn't want to stay in the positive charge. So what happens? This oxygen-hydrogen bond will be broken. And what you are going to get? RO. C, and this bond is broken, right? So the plus charge goes with the hydrogen and H plus will be released. So this is how the general reaction takes place when the alcohol is behaving as a nucleophile. OH bond will be broken. The next one is reaction involving cleavage of carbon-oxygen bond. So when there is a cleavage of carbon-oxygen bond, the alcohol will be behaving as an electrophile. Electrophile means, of course, the opposite. It will be having attraction towards negatively charged species, right? So let's take the example of CH3, CH2OH, right? Fine. So to this, it is undergoing protonation. So now the alcohol is going to undergo protonation. Protonation means what? We are going to add H plus. So what it is going to happen? See, we are going to add this H plus to the alcohol. CH3, CH2, one hydrogen here, one hydrogen here. So I have added one more hydrogen here, means the oxygen will of course get a positive charge, right? So now what happens? Your alcohol is going to behave as an electrophile. It is having a positive charge, right? So now let us consider a nucleophile Br minus. So now what happens? As alcohol is acting as a electrophile, it will have attraction towards a negatively charged species. So now what happens? What will be formed? This Br minus will be taken up by the alcohol, and this much part will be removed. That is, water will be removed from here. So what you are going to get? CH3, CH2, Br plus H2O. Water will be released. So what you can observe here, carbon-oxygen bond is broken, right? Carbon-oxygen bond is broken and water is being removed and the bromine is being attached. So I hope this is clear to you. So now we are going to discuss the reaction involving the cleavage of oxygen-hydrogen bond. So as discussed already, now the alcohol is going to behave as a nucleophile. The first one is acidity of alcohols, reaction with metals. So the first one is reaction with metals. Alcohols reacts with highly electropositive alkali metals such as sodium, potassium, aluminum, etc. to yield corresponding alkoxides with the liberation of hydrogen. So a general representation is shown here. 2 moles of your alcohol reacts with highly electropositive metals. That will be generally first group metals, right? Sodium, potassium, aluminum, etc. What happens? Sodium alkoxide will be formed. As you can see, what will happen? The sodium will be substituted here, right? The oxygen-hydrogen bond will be broken. 2 moles are there. That means what will be formed? Hydrogen gas will be liberated and the sodium will get attached with the oxygen. So this is called as alkoxide. That is RONA, sodium alkoxide. Right? I hope it is clear, and hydrogen gases evolved. Okay. Now the above reactions show that the alcohols are acidic in nature. Alcohols are acidic in nature. In fact, alcohols are Bronsted acids. That is, they can donate a proton to a strong base. They are capable of donating proton to the strong base. If they can donate proton means what? If it can donate H plus means what? Of course, it is acid, right? So alcohols are acidic in nature, right? So if this is a strong base, right, and this is your alcohol, what happens? Alcohol is able to donate its H plus. It is able to donate its H plus. So what happens? This H plus will be donated to the base. So what happens? BH, which will be the conjugate acid, and alkoxide ion will be formed. Alkoxide ion will be formed. Okay. So this is why alcohols acts as Bronsted acid, hence they are acidic in nature. Now, the acidic nature of alcohols is again due to the polarity of the OH bond, okay, as discussed already. So, an electron donating alkyl group increases the electron density on oxygen atom and decreases the polarity of OH bond, and also decreases the stability of alkoxide ion due to plus I effect. This decreases the acidic strength of alcohols. Now, the acidic strength of primary, secondary and tertiary alcohols is in the following order. So what does this mean? As discussed, there is a polarity difference between oxygen and hydrogen. Electronegativity difference is there. Hence, the oxygen-hydrogen bond is a polar bond. Now, apart from oxygen and hydrogen, you as well as have a alkyl group here. Now, alkyl groups are having plus I effect. That means they are ready to donate its electron. So, when the alkyl group is ready to donate its electron, the electron density on oxygen atom starts increasing. When the electron density starts increasing, the oxygen-hydrogen bond polarity will start decreasing. Because of that, the acidity of the alcohols becomes lesser and lesser. So, when we are considering primary, secondary and tertiary alcohol, then which will be having the highest acidity? Of course, it will be primary. Why? Because when more and more alkyl groups is added, right? When more and more alkyl groups are present, what happens? Plus I effect will be more. Oxygen will have more electron density. Hence, the bond will be less polar. Hence, it becomes difficult to break the OH bond and release the H plus ion. Hence, it will become lesser and lesser acidic. So, considering here you have only one alkyl group. Here in the secondary alcohol, you have two alkyl groups. So, density will be more and more on the oxygen atom. Hence, it becomes difficult to break this OH bond. Hence, it will be less acidic. Now, considering tertiary, there are three alkyl groups, which all of them will be having plus I effect. Now, alcohols act as Bronsted bases as well. It is due to the presence of unshared electron pairs over oxygen, which makes alcohols as proton acceptors. So, it can also act as Bronsted bases because, yes, on oxygen, what you are having lone pair of electrons. So, it is also able to donate electrons as well, right? Now, alcohols are weaker acids than water. Weaker acids than water. So, just now we discussed alcohols are having acidic character, and how does it vary in primary, secondary and tertiary. Primary is having the highest acidity, then secondary, then tertiary, because more and more alkyl groups, more will be the plus I effect. Now, comparing alcohols and water, alcohols are less acidic than water. Now, this is very important. Why alcohols are less acidic than water? Now, in alcohols, due to the electron donating nature of alkyl group, the stability of alkoxide ion decreases. So, in case of alcohols, when it is donating its H plus, that is the protons are being removed, what happens? Alkoxide ion is formed. So, when alkoxide ion is formed, its stability keeps decreasing. So, as you can see here, this is ethanol. Now, what happens when H plus is released? It forms an alkoxide, that is CH3CH2O minus. This is an alkoxide. So, its stability decreases, hence acidity will be less. But in case of water, OH minus ion is formed by its ionization. It is more stable than alkoxide ion due to the absence of electron donating group, right? So, in this case, as you can see, you have an alkyl group which will donate its electron, right? It will show plus I effect, hence the stability will decrease. But in case of water, what is that you are forming? OH minus, H plus will be released, OH minus will be formed. Now, in the case of OH minus, do you have any alkyl group? No. So, of course, it won't be donating any electron, there is no alkyl group. Because of that, when you are comparing alkoxide ion and hydroxyl ion, that is alkoxide, R O minus and your OH minus. OH minus will be more stable because it doesn't have an alkyl group. Hence, alcohols are weaker acids than water. So this is very important to remember what is the reason. Now, moving on to the next set of reaction, that is esterification of alcohols. So esters are produced when alcohols are heated with carboxylic acids in the presence of an acid catalyst. This reaction is called as esterification. So using esterification method, we are going to produce ester itself, right? So that is your alcohol and acid is going to react in presence of an acid catalyst, so to form an ester. The catalyst is usually concentrated sulfuric acid or dry HCl. The function of concentrated sulfuric acid is to act as a protonating agent. It is acting as a protonating agent. That means it will be ready to donate its H plus as well as a dehydrating agent. Dehydrating means it will remove the water molecules. So the reaction is reversible and equilibrium can be shifted towards the forward direction by removing water as soon as it is formed. So it can happen in the both ways, that is alcohol and acid will combine to form ester, as well as ester and water can combine to form alcohol and carboxylic acid, right? So this is the carboxylic acid which is shown here, RCOOOH, right? And this is your alcohol, R-OH. Now what happens? As said, concentrated sulfuric acid is used. It's a dehydrating agent. Water will be removed. H from the alcohol and OH from the carboxylic acid is removed. Now what is left behind? RC double bond O R dash. That is RCOO R dash. So what is this? This is the ester which is formed, right? And water is being removed, right? Now the ester can react with water and again it can form back the alcohol and carboxylic acid. So this is a reversible reaction, right? So few examples is shown here. Acetic acid, CH3COOH, and you have methanol. Again, hydrogen from the methanol and hydroxyl group from the carboxylic acid minus H2O. Water will be removed from here. Sulfuric acid is a dehydrating agent. So you get CH3C double bond OCH3, right? So that is methyl acetate, which is the ester, and water, right? So you can see a double-sided arrow here. It shows that it is a reversible reaction. Now you have acetic acid and ethyl alcohol. Ethyl alcohol is taken. Again, water is being removed. You get CH3C double bond O, CH2, CH3. So what you have to remember, this reaction is very simple. OH from the carboxylic acid and H from the alcohol has to be removed. So if you write it in the reverse direction, it will be easy for you to remove the H2O. And what else is left behind? You can combine it and write, you will get an ester, right? The next one is benzoic acid is taken here. Even here, you can see the benzene ring C double bond OH, and ethanol is taken here. So again, water will be removed. You will get the benzene here, C double bond OCH2, CH3. That is ethyl benzoate. So this is esterification reaction. Now the next reaction is acylation of alcohols. Acylation means we are going to add an acyl group. Okay, we are going to add an acyl group. Now what is going to happen in here also? You are going to get ester. So there are two methods. Once you can add carboxylic acid and form an ester. Another one we are going to discuss now. Esters can also be obtained by treating alcohols with acid chlorides or acid anhydrides. The reaction with acid chloride is carried out in the presence of pyridine base so as to neutralize HCl, which is formed during the reaction. The introduction of acetyl group in alcohols is called as acetylation. So acylation and acetylation is the same. So what is happening here? Alcohol is taken, acid chloride. Now what is acid chloride? RCOOH is your carboxylic acid. The OH is replaced by a chlorine. So you get RCOCl, right? OH is replaced by Cl. So that is called as acid chloride in presence of pyridine. Why pyridine is used? That reason is also given here to remove this HCl, which is formed as a byproduct. So what is happening here? H and Cl will be removed. As you can see, for example, I have shown here ROH, that is your alcohol, and you have your acid chloride. Okay, which is written in this format. Now what happens? This HCl will be removed. You get RC double bond O R dash. So this is your ester. HCl will be removed, and that can be removed from this product which is formed using pyridine. So you have methyl alcohol CH3OH methanol, and acid chloride is taken, hydrogen and chlorine will be removed, HCl will be removed. You have CH3, C double bond O, CH3. Okay, so this is methyl acetate which is found, and you have ethyl alcohol and acetyl chloride. Again, hydrogen and chlorine will be removed. You get C2H5, C double bond O, CH3. So this is ethyl acetate. So there are two methods in which you can form esters. So these are two different reactions of alcohols. Next one is oxidation using PCC, pyridinium chlorochromate. So oxidation, again we are going to add oxygen. So let's see exactly what is going to happen. Are we going to add oxygen here? Another way we can discuss in terms of oxygen, right? It can be removal of hydrogen also. It can be addition of oxygen or else removal of hydrogen. So oxidation of alcohols involves the formation of a carbon-oxygen double bond with the cleavage of oxygen-hydrogen bond and carbon-hydrogen bond. So as you can see, alcohol is shown here. This can be any other group. Let's fill in it with hydrogen itself. So this is your methanol. Now what happens? A cleavage will happen between oxygen-hydrogen bond as well as carbon-hydrogen bond also. So now what happens? Hydrogen will be released. That means H2 will be removed. That is also oxidation, right? Hydrogen will be removed from here and you will get a double bond. That means let's assume this hydrogen is removed and this hydrogen is removed. Hydrogen is being removed. So what happens? There will become a double bond between the carbon and oxygen which is shown here. These reactions are also called as dehydrogenation reaction due to the loss of two hydrogen atoms from the alcohol molecules. So oxidation, you can remember it as removal of hydrogen atoms. So this is also called as dehydrogenation. Okay. Now first one in that is oxidation of primary alcohols. Okay. So a primary alcohol is easily oxidized to form first an aldehyde and then a carboxylic acid in the presence of strong oxidizing agents like acidified potassium permanganate solution, that is KMNO4, or acidified potassium dichromate solution, that is K2Cr2O7. So you can either use acidified KMNO4 or else K2Cr2O7. So what is that written here? Alcohol can be oxidized to aldehydes first, and then it is oxidized to carboxylic acid. It's a stepwise process and we have to use a strong oxidizing agent, right? Like alkaline KMNO4 or K2Cr2O7. So you have the alcohol here. It undergoes oxidation. Oxidation we have just discussed now. Hydrogen will be removed. Two atoms of hydrogen. So let me write it in this format. RCH2OH. Now it is going to undergo oxidation. This stands for oxidation. Oxidation is going to happen. This hydrogen is removed. Another hydrogen is removed. Now what happens? These two hydrogen is removed. So the carbon will have only 3 bonds. So of course it has to form a double bond. So what you are going to get? RCH and double bond O. Now what is RCHO? It is an aldehyde, right? Again it undergoes oxidation. We are going to add an oxygen here. So what you are going to get? RCOH and you have double bond O. That is RCOOH, which is your carboxylic acid. I hope it is clear. So what you have to remember, first you will be having alcohol. It undergoes oxidation, forms aldehyde. It undergoes oxidation and forms carboxylic acid, right? Now oxidation of primary alcohols to aldehyde stage can be stopped by mild oxidizing agents such as PCC, pyridinium chlorochromate. It is a complex of chromium trioxide with pyridine and HCl. By using this reagent, aldehydes can be isolated in these reactions. So as discussed now, if we are using strong oxidizing agent, what will happen? Alcohols will oxidize to aldehydes, aldehydes will oxidize to carboxylic acid. So from alcohols, you will get carboxylic acid and the reaction will stop. So this will be your final product. So if we require only aldehyde, we want to stop the reaction at this step. That is alcohol, I want to oxidize and form an aldehyde. I don't require a carboxylic acid. Then what can be done? The reaction should only end here. This should not be formed. Then we can use the reagent. That is PCC, pyridinium chlorochromate, can be used instead of strong oxidizing agent KMNO4 and K2Cr2O7. Strong oxidizing agent will give you carboxylic acid. Mild oxidizing agent like PCC will give you aldehyde and will stop the reaction. So you have but2-in-1-ol here. So now in the presence of PCC, what happens? So let me write down this here. CH3, CH double bond, CH2. OH. Okay. Now, in the presence of PCC, we'll just get the aldehyde and the reaction will stop. So, one hydrogen will be removed from here, another will be removed from here. You'll get C double bond O. That is CH3, CH double bond CH, C double bond OH, CHO will be formed. An aldehyde will be formed, right? Now, the next one is oxidation of secondary alcohol. Primary alcohol will give you aldehyde first, then carboxylic acid if you are using a strong oxidizing agent. If you are using mild one, you will get the aldehyde. Now, secondary alcohols are oxidized to ketones by chromic anhydride, that is CrO3. Okay, so if you are using CrO3 in secondary alcohol, you are going to get a ketone. So this is a secondary alcohol. You can see the hydroxyl group attached to the carbon, which is attached to further two other carbon atoms. So this is a secondary alcohol. Now, in presence of CrO3, what happens? Yes, again hydrogen will be removed. One hydrogen from here, one hydrogen from here. So you will get a double bond here, which is ketone, right? C double bond O. So this is a ketone. So you have another example here, isopropyl alcohol. Again, oxidation is taking place, right? CrO3 is also oxidizing agent. So these two hydrogen will be removed. You get a acetone here, which is again a ketone, right? Now, next one is further oxidation of ketones under drastic conditions forms carboxylic acid with lesser number of carbon atoms. Okay. Now, once the ketone is obtained, it can further undergo oxidation and form carboxylic acid as well. But these carboxylic acid which is formed will have one carbon atom less. Okay. So, under drastic conditions, what is going to happen? As you can see, the ketone will form a carboxylic acid. So, you can see here CH3CO, CH3 acetone is taken. You are going to get acetic acid. Okay. So, oxygen will be added to this and you are going to get the corresponding carboxylic acid. Now, tertiary alcohol. So, primary and secondary already discussed. Primary will give you aldehyde and carboxylic acid. Secondary will give you ketone, right? Tertiary alcohols do not undergo oxidation reaction easily under drastic condition, that is if you are using strong oxidizing agent like potassium permanganate at elevated temperatures, cleavage of carbon-carbon bond takes place and a mixture of carboxylic acid containing lesser number of carbon atoms is formed. So, a tertiary alcohol is shown here. Oxidation is going to take place in drastic condition. That means strong oxidizing agent at very high temperature. So, what you are going to get? So, first the ketone will be formed by the breakage of the carbon and another carbon. This alkyl also stands for carbon itself, right? So, that is alkyl groups, right? So, it will be also containing carbon. So, this carbon-carbon bond will break and this hydrogen will be removed. So, what you are going to get? A ketone you are going to get. Again, it is going to undergo oxidation. You know that. The ketone will undergo oxidation and forms what? Carboxylic acid. Now, another specific example, tertiary butyl alcohol it is taken. So, what you will get? Acetone you will get. This CH3 and H will be removed, right? So, what happens? You are going to get CH3CCH3 double bond O, that is your acetone, which undergoes further oxidation to form acetic acid. So, as you can see in this, initially you were having 3 carbon atoms. That means in total 4 carbon atoms. But your ketone is having only 1, 2, 3 carbon atoms. The acid is also having lesser number of carbon atoms. So, here also you can see initially there were 4 carbon atoms and then you have only 3 and finally you have only 2 carbon atoms. So, there will be lesser and lesser number of carbon atoms as you proceed this oxidation. I hope it is clear, right? Now, in the next session, we are going to discuss the reaction involving cleavage of carbon-oxygen bond, right? Today, we discussed cleavage of oxygen-hydrogen bond. Next session, we are going to discuss the cleavage of carbon-oxygen bond. That is, your alcohol is going to act as an electrophile. So, I hope the concepts that we have discussed in this session is clear for you. So, that's all for today. Thank you.